Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. And within this module, we are trying to understand how does the operating system manage the CPU by providing this abstraction of a process, right? And within the second module, we are currently on the third topic, that is system calls, exceptions, and interrupts. So, as you know, in this topic, we have been talking about the three different kinds of events. So, till now, we have only talked about system calls and exceptions in the previous videos. In this video, I want to introduce the concept of interrupts, right? So, without further ado, let's get started. So now let us understand what are interrupts, right? So here I have the definition of interrupts. So let me read it for you. So an interrupt is a signal, right, from a hardware device or software to alert the CPU about an event that needs immediate attention from the operating system, right? And the next thing is that the interrupt causes the CPU to stop the current flow of execution and force the transfer of control to a special code routine in the kernel to handle that event, right? So this definition basically, first of all, an interrupt, right, as it says, it's a signal, right? So why do we need a signal? The signal is basically to alert the CPU or the processor. It has to, the signal's purpose is to notify the processor about an event, right? It is an event that needs immediate attention from the operating system. Also, this signal can come from either a hardware device, that is, it could be an input output device, right? Or this signal can come from a piece of software, that is the user programs that are executing on the CPU, right? So this signal alerts the CPU about an event or a situation that needs immediate attention from the operating system, right? So when the CPU detects this signal, when the CPU detects the interrupt, what it does is that it stops doing what it was doing, right? It basically would be executing some user process. So when it detects an interrupt, it pauses or halts that user process and immediately forces the transfer of control of the execution to the operating system. Basically, it stops what it was doing. It stops executing the instructions of the user process and transfers the control to the operating system, right? And then the operating system executes a special piece of code, or we can say a special routine that basically handles the interrupt. Basically, it takes certain action in context of the event that is there, right? So the basic source of the interrupt was that there is an event that needs immediate attention from the operating system. So once the operating system has the control, it will do whatever is necessary, because whatever attention it required from the operating system, it basically required some assistance or some action from the operating system. So in that special routine, it's special piece of code, the operating system will perform that action in order to deal with that event. So this is what is an interrupt and how it is handled in the computer system, right? So this slide talks about the different kinds of interrupts that are there, right? So interrupts can be classified into two types. One is software interrupts and the other is hardware interrupts. So as the name suggests, software interrupts are basically the source of these kind of interrupts is the software, right? The user processes that are being executed on the CPU, they cause these kinds of interrupts. And examples of software interrupts are system calls and exceptions. So we have already talked about system calls and exceptions, and we know that in case of a system call, it is the user process which requests which is requesting the operating system to perform a certain operation on its behalf, right? So a system call is arising from the user process, and it is a type of software interrupt. Similarly, in case of exceptions, it is the error or the unexpected event in the context of the user process that is being executed. Basically, in case of exceptions, the user process misbehaves, and that is why the CPU basically brings in the operating system into the picture to deal with that error or an unexpected event. In both the cases, in both system calls and exceptions, the source of interruption is a piece of software, right? The other type of interrupts that exists is called hardware interrupts. Hardware interrupts arise from hardware devices like input output devices, right? These interrupts are basically meant to signal or notify the CPU that there exists a situation or some event has happened in one of these hardware devices which needs to be immediately attended to by the operating system. And examples of hardware interrupts are device interrupts. So we'll study the device interrupts in great detail in this video. So now what we will do, we'll quickly go over system calls, exceptions, and device interrupts and see how all of them fit into this definition of interrupts. So let us first talk about system calls. So this is the timeline diagram of a system call that we have been talking about since in the previous videos also. So if you see what is happening in the case of a system call, right? The user process is executing instructions and then it invokes a system call. And we know that for invoking a system call, it executes a trap instruction. The trap instruction immediately transfers the control of execution to the operating system. So now, as we discussed about interrupts, so what did we say about interrupt? We said that the interrupt is a signal, right? And it could come either from the hardware or the software. So you can see here the user process, which is a piece of software. It is signaling, like generating a signal via the trap instruction for the operating system that I want to execute. I want this particular system call or this operation to be performed on my behalf, right? And when this signal is there, what the CPU does, basically in this case, this signal comes via a trap instruction. Whenever there is a trap instruction, the CPU immediately stops what it was doing. So CPU was basically executing the instructions of this user process. It pauses this user process and transfers the control to the operating system. And when the operating system has the control of the CPU, it executes a special routine to handle the basically the signal, in this case the interrupt. So here the signal or the interrupt that the user process has raised, it is kind of requesting the operating system to perform the system call. So which system call? The read system call. So what the operating system will do, it will execute the read system call, which will read some data from some file, right? So this is how a system call is a software interrupt. It is a signal that is generated from the user process, which is a piece of software. When the user process executes the trap instruction, the CPU pauses the user process and immediately transfers control to the operating system. And in response to this software interrupt, this request for a system call, the operating system executes the routine of the read system call to handle this event. Next, let us talk about exceptions, right? So we discussed that an exception is also a software interrupt, right? So first of all, you can see the exception happens when the user process misbehaves. There is some kind of error or there is some kind of unexpected event, right? In this case, you can see the user process is trying to divide by zero, which is an illegal operation. So again, when the user process tries to do this, the CPU detects that this is an error, which needs immediate attention from the operating system. So here, what the CPU does is that it immediately transfers the control of execution to the operating system. In this case, we do not have a trap instruction. The transfer of control is taken care of by the CPU itself. Whenever it detects an event that can be called an exception, then it immediately forcefully transfers the control to the operating system, right? And the operating system then deals with this exception via a variety of ways. It has different options. Either it can terminate the offending process, or as we discussed, it can handle it in a graceful way, or it can let the user process itself handle the exception, right? So again, as you can see here, the different features or properties that we discussed about a software interrupt holds true. First of all, the source of exception, right? Here the source is the software. The user process was executing, and the reason why we have an interrupt in the system is because the user process misbehaved. The source of the interrupt is the software, right? The user process that misbehaved. And in response to that misbehavior, in response to that event, the CPU immediately transferred the control of execution to the operating system. And finally, the operating system executes a special routine, which we call the exception handler, right? So the exception handler basically tries to take a corrective action in order to deal with the exception. So the exception this exception handling kind of guarantees that the system functions in a proper and expected way. So again, the point is that the properties of software interrupt that we discussed hold true for an exception, right? So both the system call and the exception are types of software interrupt, right? They are signifying that there is some condition or some event that needs immediate attention from the operating system. In case of system calls, the immediate attention was in the context that the software, the user process that is executing, it needs a it needs some operation to be performed on its behalf. In the case of exceptions, the situation that needs immediate attention is that the piece of software, the user process that was executing, it misbehaved or something, it needs something, right? And then finally, once the control is transferred to the operating system, then the operating system executes the appropriate special routine. In case of a system call, it executes the system call function body, right? The system call routine, right? And in case of the exception, the operating system will execute the appropriate exception handler, right? So this was about system calls and exceptions and overall the software interrupts. Next we'll talk about hardware interrupts, which are generated by IO devices and other pieces of hardware. So now let us shift our attention to the second type of interrupts that are there, that is hardware interrupts, right? So an example of hardware interrupts are device interrupts. So as we already discussed, hardware interrupts are signals that are generated from hardware devices, the IO devices, to alert the CPU that there exists some situation or an event that needs immediate attention from the operating system. So to understand and see device interrupts, we have to first understand something which is called interrupt driven IO. So now we will study interrupt driven IO through an example, and interrupt driven IO are the major source of hardware interrupts. So understanding this is important if you want to understand hardware interrupts. So now we'll understand interrupt driven IO with an example, right? So the point is that we want to perform an IO operation and leverage the interrupt mechanism to make it more efficient, right? So let's start with this example. So as you can see, there are again two parts to this diagram. The blue region indicates that currently we are executing the instructions of user process, and let us assume that currently some process A is executing on the CPU. This is the CPU, and this is the kernel region. Basically here we will be showing when the operating system comes into the picture, when we are executing the operating system code, right? And here we have a IO device, that is the hard disk. And as you know, the hard disk is a persistent storage where we store our data in form of files, right? And this is the hard disk controller, or you can say device controller, which is responsible for managing the hard disk. So as we have already discussed in the previous videos, that the device controller is a piece of electronic chip that is responsible for managing and controlling the associated IO device. So now let us start the let us see how the process A it will be performing the IO operation using the mechanism of interrupts. So let us assume that the process A requests for an IO operation to be performed, right? It wants to read some data from a file on the hard disk. So it invokes the read system call, right? So in the read system call, the operating system will basically initiate a read operation from that particular file that is present on the hard disk. So when this system call is invoked, as you know, the control of the CPU is immediately transferred to the operating system, and then the operating system will basically initiate the IO operation, right? It will basically first of all give instructions to the device controller, like from which file the data has to be read, how much data has to be read, right? The mode of operation, all of these pieces of instructions the operating system will give to the device controller. It will basically program the device controller to initiate the IO operation. And once the operating system has programmed the device controller, then the device controller starts the operation from the hard disk. So since this is a read operation, the device controller will be basically there will be a copy operation, that is data will be transferred from the hard disk to the local storage of the device controller, right? So as you can see, this IO operation is like currently in progress. So now in the meanwhile, when this copy is taking place, what the operating system does is that it switches to some first of all it puts the current process, that is process A, into waiting state, and then switches to some another process, right? Let's assume that this is some process B, right? So why does the operating system do this? Let's first understand this. So the reason why the process A was put to sleep and some other process, like the operating system selected some other process to run, is that the basic idea is that IO devices are very slow, right? So if you see this copy operation, then it will take a few milliseconds to copy that data from the disk to the device controller, right? So the speed of the modern hard disk are in the order of few milliseconds, right? But now the problem here is that these few milliseconds are way too much from the perspective of the CPU. The speed of the CPU is much higher than that of IO devices. In this span of few milliseconds, the CPU is capable of executing hundreds and thousands of instruction, right? So now we have two options. The first option is that process A is allowed to execute, but since process A needs that data, right? It needs that data from the file to basically further process that data. So it won't be able to do that processing unless that data is available. So what process A will do, it will just continuously check or poll the IO device that whether the operation that it had requested is complete or not. So all it will do, all process A will do is that it will continuously check for those whole duration of those few milliseconds. It will use the CPU to do this simple task of checking whether the operation is complete or not. Basically, we can say it is like spinning in a while loop or some kind of loop and just checking whether the operation was complete or not. And this is like we can say that there is no useful work being done here by process A. So we can say that the CPU cycles have been wasted, will be wasted if process A is given the control of the CPU for those few milliseconds while this copy is happening, right? So this is the first option. The second option is that what we can do is that while this copy is happening, we can put process A to sleep. We'll pause process A for some while and then give the CPU to some other process. Let's say process B, which is ready to execute instructions. That is, it can do processing. It is not waiting for any operation to complete, right? So that is what the operating system does. It makes a wiser decision. It puts process A to sleep and then allocates the CPU to some other process, right? So as you can see, in the meanwhile, when this process B is executing, right, both the IO device is also working and the CPU is also executing instructions. So there is a overlap of operations. So IO operation and computation on the CPU, both of them are happening in parallel. So you can see this is a much better utilization of resources compared to the case if we had allocated the CPU to process A. Their process A would not be doing any meaningful or useful work. It will just be spinning on the CPU to check whether the operation is complete or not, right? So that will be a lot of like hundreds and thousands of instructions just wasted on checking on the status of the IO operation. So that is why the operating system allocates the CPU to some other ready process. So now the next thing that happens is that the, let's say the copy operation has finished. As you can see, this copy is done and the data has been processed by the device controller and now it is ready for consumption by process A, right? So but now, as you know, the process A is in the waiting state. It has been put to sleep, and also process A is not currently running on the CPU. It's some other process, that is process B. So once the transfer between the controller and the device, this is the controller and this is the device, once the transfer here is completed, then the next thing that the device controller does is that it raises an interrupt to the CPU. So this is where you see how interrupts are useful, right? You can see that here the device controller, which is a piece of hardware, it is signaling, it is raising a signal to alert or notify the processor that there is a like there is an event which needs immediate attention from the operating system. So what is that event? The event here that needs attention from the operating system is that the IO operation which had been requested by process A, that has completed. So now the operating system, now it is a good thing that it would be a good thing to do that the operating system should come into the picture. It should wake the process A that had been put to sleep and also copy this data from the controller to the DRAM for the consumption of process A, so that process A can continue its processing, right? So that is why the device controller raises an interrupt so that the operating system can process the data, right? So once the CPU detects that there has been an interrupt, the next thing that the CPU does is that it starts acting upon it, right? So the CPU, once it decides to handle the interrupt, it immediately halts the current process. That is, it immediately halts whatever it was doing. In this case, it was executing process B. So process B execution is paused and the CPU immediately transfers the control to the operating system. So this is a forced transfer of control, right? So the control will now be transferred to the operating system and here you can see the operating system code is being executed. So what the operating system will do, it will execute a special piece of routine which we know as interrupt service routine. And the point here is that we have to handle the interrupt. The device controller had raised an interrupt to signify about an event, right? So the operating system has to take appropriate action. So what the operating system will do, it will check which device had caused the interrupt. It will figure out, okay, the hard disk had raised an interrupt, and it will check the device controller registers, and it will find out, okay, an IO operation that had been requested earlier, it has completed, right? So what it will do, it will kind of finish this operation by copying the data from the device controller's local storage to the DRAM, right? From the DRAM, the process A can consume it. But as you know, process A is currently sleeping. So the operating system will wake up the process. It will shift the process A from waiting state to ready state. Once it is in the ready state, then it can be allowed to run on the CPU. And finally, after unblocking the process, the operating system clears the interrupt. That is, in a way, we can say it acknowledges the interrupt. Now that the operating system has handled the interrupt, the next thing the operating system does is that now it has to transition back to the user space, right? Its work in the kernel space, it's done. So now the next step is that operating system has to transition to some, like, give the control of the CPU to some user process. So the question here is that which user process should run next, right? It could be actually there are several options here. The operating system can select process A also for execution, because process A had requested the read operation, and now since the data, the IO operation has completed, it's a good idea to run process A. Or process B can also be allowed to run because it was anyway executing on the CPU. It had been interrupted, and the operating system can choose process B also. And another option is that the operating system can select some other process, not A, not B, but some other process, depending on whatever policy the operating system follows. With whatever is the case, eventually process A will get the CPU after some time. If not this time, after some time, the control will be given back to process A, then it can consume the data that it had requested for. So the point is that after handling the interrupt, the operating system will call the scheduler, which we will study about in the upcoming videos, which is basically a piece of software that selects the user process that should be allocated the CPU next. And then once this selection has been done, once it is decided that to which user process should the CPU be allocated, the control is then transferred to that particular user process. So this completes the interrupt driven IO, right? We now have a good idea of what is an interrupt driven IO. So basically, let me summarize it for you. It is basically a mechanism where the user process initiates an IO operation. And since the IO operation will take some time, IO devices are slow. Instead of wasting CPU cycles by just checking whether the operation has completed or not, what the operating system does is that it pauses that process which had requested the IO operation, right? In this case, we saw process A, and gives the control to some other user process. That is, here in this case, it was process B. So now what happens is that both the IO operation and the computation on the CPU proceed in parallel. This overlap of IO with compute leads to, like, a better utilization of the resources. CPU is also a resource. The copy bandwidth of IO is also a resource. So both the operations can go on in parallel, right? And the interrupt mechanism comes into help here, right? Once the operation is complete, the interrupt mechanism is used to notify the CPU, and then process A can be brought back into the picture. If we did not have the interrupt mechanism, then this efficiency would not have been possible, right? So by using this interrupt driven IO, we have more efficient computer system where IO operation and compute can happen in parallel. And the interrupts that arise from this interrupt driven IO are a major source of hardware interrupts. So now we'll look at some other sources of hardware interrupts also, like what are the different reasons why hardware devices raise the interrupts. So in the previous slides, we just talked about interrupt driven IO. And in order to understand interrupt driven IO in a better way, I have a interesting analogy for you. So if you see interrupts, it's not just that interrupts happen in the context of computer system. There are many events that happen with us in our daily life that can be correlated with the concept of interrupts, right? So just to give you an analogy of interrupt driven IO, think of how you use a washing machine or a microwave oven, right? So let's consider the case of the washing machine. Let's say you have to wash some clothes. So what you do is that you put your clothes in the washing machine, you put the detergent, and then you like program, like give the appropriate settings to the washing machine, and then you hit start, right? And now that the washing is going on, once the washing of clothes has started, you don't stand there and wait for it to complete, right? You just don't, you then go on to do some other work, right? And once the washing has been done, after let's say half an hour or 45 minutes, then it rings a bell or an alarm kind of sound, which notifies that, okay, the washing of clothes has been done. Now you can take out your clothes. So then when you hear the bell, you come back, and then that is when you take out the clothes from the machine. So if you compare this, this is very similar to how interrupt driven IO works. You start the IO operation, and then you do not wait for the operation to complete. The operating system then like switches to some other work. That is, it allocates the CPU to some other process different from the one which had initiated the IO operation. So here basically the CPU is optimizing the work. The CPU is not like being allocated to some user process which will only spend time checking the status. It is being allocated to some other user process which will do some meaningful work, right? So that both the IO operation and the computation can go on in parallel. And when the operation is complete, then the operating system can come into the picture and deal with the like data. So in a similar way, in the case of washing machine, here you do not kind of like once you have initiated the washing process, you do not stand there for the washing to complete. You can go on and do your work, and in the background the washing machine will also be washing the clothes. So both the washing of clothes, and let's say you are studying and you being like doing the study, both of them can go on in parallel. And once the machine has done its job, it can notify you, it can interrupt you with a alarm or a sound, right? So this is how the washing of clothes is very similar to how interrupt driven IO works. Similarly, in the case of the microwave oven, you can imagine how it is very similar to interrupt driven IO. You put the food in the oven, and then you like just like the washing machine, you program it in a proper way, and then you start the oven. So in the meanwhile that the cooking is happening, you don't stand there and watch the like wait for the cooking to finish. You go on and do some other work. Let's again assume that you want to study. So you went on and you were doing your study, and the microwave oven was also cooking the food in parallel. Both of these operations are going in parallel. And once the cooking is finished, then the microwave oven, just like the washing machine, interrupts you or notifies you with a alarm or a sound. Then you can come back and take your food and then have your meal, right? So this these two examples, that is one of the washing machine and the other of the microwave oven, gives you like a better understanding of how interrupt driven IO works. So now that we have talked about interrupt driven IO, let's shift our attention back to the uh, different types of interrupts that we want to study, right? So in the case of the computer system, when we talk about device interrupts, then there are two types of interrupts. One is expected device interrupts, and the other type of interrupts is random device interrupts. So first we'll talk about expected device interrupts, and then in the next slide we'll talk about random device interrupts. So the IO devices which follow the interrupt driven IO, right? The interrupts that they raise, they come under the class of expected device interrupts. Why is it the case? Right. So we just talked about interrupt driven IO, right? So let me explain this with an example. When you start the washing machine, then you are expecting that after some time the washing machine will alert you that the washing is complete. So the notification that comes from the washing machine, or the interrupt that comes from the washing machine, is an expected interrupt. You have started the operation, right? That is why there is going to be an interrupt. So you are expecting that interrupt to happen in some at some newer point in the future. Okay. Similarly, in the case of the microwave oven, it is you have who has put the food in the oven, right, and started the cooking process. Again, in the case of the oven also, you are expecting that the oven should notify you after some time that the cooking is done. The same is the case with interrupt driven IO. When the operating system initiates the IO operation on behalf of the user process, right, it is expecting that once the IO operation is complete, after some time there should be a notification, right? And when that notification or the interrupt comes from the CPU, basically the device will raise the interrupt to the CPU, and the CPU will bring the operating system into the picture. That is when the operating system will handle the interrupt and execute the interrupt service routine and do all of those things. So just like you're expecting the interrupt from the washing machine so that you can take out the clothes, or you're expecting the interrupt from the microwave oven so that you can take your food, in the same way the operating system is expecting the IO device to interrupt once the data is available so that it can unlock the user process who was waiting for the data for processing, right? So interrupt driven IO, all of the devices that follow interrupt driven IO, the interrupts that they raise, that comes under the, like, they are a kind of expected device interrupts, right? So here, as you can see, the hard disk or the monitor, the speaker, all of these are IO devices, and they follow the interrupt driven IO technique, right? And the interrupts that these IO devices which they will generate, they are a kind of expected device interrupts. It's the operating system who initiates the IO operation on these IO devices on behalf of the user process. So once the IO operation is complete, when there is an interrupt, it is kind of expected by the operating system. That is why it has a dedicated interrupt service routine, right? So this was the first type of interrupt. Another example that I wanted to cover here is the timer interrupt. So the timer is a special type of device. It is not an IO device, but it's a special piece of hardware that exists on all computers. We will study about timers in great detail when we talk about CPU scheduling. But the concept of the timer is that during the boot process, the operating system programs the timer or configures the timer to raise interrupts at a like fixed interval of time, right? Let's say after every 100 milliseconds, the timer is supposed to raise an interrupt, right? This is how the operating system programs the timer interrupt. And then once the timer raises an interrupt, what the operating system does is that it uses that opportunity, that so you know that whenever there is an interrupt in the system, the control will be immediately given to the operating system. So the timer interrupt is used by the operating system to run the scheduler so that there can be a change in the like allocation of the CPU. So whichever user process was executing on the CPU, then the operating system can decide to change that user process, right? So this is basically related to the time sharing of the CPU, right? We have discussed about time sharing in great detail in the previous videos. So again, when we talk about CPU scheduling in the next in the upcoming topics, we'll come back to timer interrupt. But why am I talking about timer interrupt here? The reason is that timer interrupt is also a kind of expected interrupts. It is the operating system who configures, or we can say it is the operating system which programs the timer to raise the interrupt after every few milliseconds, right? So again, just like interrupt driven IO, although the timer is not an IO device and the timer does not follow this interrupt driven IO pattern, it is a special device which raises interrupts, and it is the operating system which has configured it to do so. So in all these cases, it's the operating system which kind of initiates all of these devices or starts some operation on these devices. And when the like the condition is met, then they raise an interrupt, right? So all of these interrupts that come, first of all of these are hardware interrupts, these are device interrupts. And the second thing is that the nature of these interrupts are kind of, they are expected, so they are they can be classified as expected device interrupts. So after having talked about expected device interrupts, let us shift our attention to the other type of interrupts that exist, that is random device interrupts. So in order to understand random device interrupts, I will again take some examples from our daily lives, and these examples from daily lives will help us to understand the nature of random device interrupts in a better way. So let's take the first example. Let's say you are at your home and you're doing your work and you're not expecting anyone to arrive, but then someone rings your doorbell, right? So in a way, you are interrupted. You have to immediately go to the door and answer the door. So when you go there, you discover that your neighbor has arrived and they have some doubt they wanted to ask, right? So here you can see you were not expecting anybody to arrive, but your neighbor had some doubt, so they came and asked you, right? So this is a kind of interrupt that happened at random. You're not expecting anything. Unlike the case of the washing machine, where you were the person who had initiated the washing of clothes, or in the case of the microwave oven, where you had initiated the process of cooking, and in both the cases, you were expecting the machines to interrupt you. In this case, you're not expecting anyone to arrive, but yes, somebody arrived at your door and you have to answer the door, right? The next example that I have is that, let's say again you're working at your home and suddenly your friend calls you. They have called for no specific reason. They just want to talk to you, right? So again, when the phone rings, that call is basically, it interrupts you, and then you answer the call and then you talk with your friend. In both the cases, uh, in the first case when the someone was at your door, and the second case when your friend called you, in both the cases you were interrupted in some way, right? In the first case, the doorbell was the sign of interruption. In the second case, the phone call was the interruption, and you were not expecting these interruptions to happen. But nonetheless, when you were interrupted, you did something. You paid immediate attention to these events. In the first case, you went to the door and then interacted with your neighbor. In the second case, you answered the phone call and talked with your friend. So this kind of gives you a better idea of what are random interrupts. Here you're not the one who had initiated anything or were expecting some like interrupt. If you compare this with the washing machine and the micro oven example, there you were the one who had initiated the process and were kind of actually expecting the interrupt to happen. So now that we have a basic idea of how random interrupts look like in real life, let us talk about some random device interrupts in the context of the computer system. So for this, I'll take the examples of a few input devices like the mouse, keyboard, and the network adapter. So mouse and keyboard, you obviously know. The network adapter is basically the piece of hardware where the internet packets, network packets arrive or they are sent from, right? This acts both like an input and an output device. But for the time being, let's consider focus the part where it is receiving the network packets as an input device. So in all of these devices, the input can arrive at any random time. Like let's take the case of the mouse. The user, let's say currently I'm moving the mouse and immediately I can see the movement of the cursor on the screen. So the thing with the mouse is that the user can move the mouse at any random time and the operating system is not actually expecting the mouse movement. It just arrives at an instant, right? And when it arrives, the operating system has to pay immediate attention and then process the mouse positions so that it can display them on the screen, right? Let's now talk about the keyboard. Just like the mouse, it's an input device and the user sitting in front of the keyboard can press the key buttons at any random time. The operating system is not expecting the key presses to arrive, but it arrives at any instant. And when it does, then the operating system has to process those keystrokes, right? They could be some form of input that has to be displayed on the screen, or they could be some kind of control characters for which the operating system has to take some action, right? Lastly, this network adapter, here also the nature of arrival of network packets is random. From the internet, the packets can arrive at any random time, right? Let's say your friend sends an email and that network packet can arrive at any time. So here in all of these cases, these are input devices and the input can arrive at any random time. The nature of these interrupts is that it is not expected. The operating system has not initiated anything like in the previous case, in the case of interrupt driven IO. The operation had been initiated by the operating system and it was kind of expecting the interrupt to arrive. In this case, it's just random, right? Other examples of random device interrupts are like not from input devices. Let's take the case of your laptop battery, right? When your laptop battery is low, you can see a notification from your operating system asking you to plug in the charger, right? Why is this the case? Because if you do not do so, then your system will shut down abruptly, which can lead to an inconsistent state, right? So in order to avoid those kind of situations, the battery has a interrupt mechanism, uses an interrupt mechanism, so that whenever the battery level, the charge level in the battery goes below a certain critical threshold, it raises an interrupt. This would be a high priority interrupt and the CPU will immediately bring in the operating system, and then the operating system will notify the user because it's very important and it has to be done urgently, so that the user can be notified that it is a good time to plug in the charger, right? So you can see random interrupts can arrive from devices which are not input output devices as well, right? And the last example that I have is that of your computer overheating, right? So in every computer, there is a thermal sensor, a thermal unit, we can say, which monitors the temperature of the chip. And if the temperature of the chip goes beyond a certain level, right, it goes too high, then the temperature unit again raises an interrupt and which brings the operating system into the picture. So in those cases, the operating system would turn on the fan of the computer so that the system, like the overall chip, can cool down, right? So this heating can occur for a number of reasons. Maybe you're running a very heavy application like a game or something, or your chip has become old and it overheats on its own, right? Those kind of things also happen. So whatever is the case for the heating of the chip, it's not a good situation, because if the chip temperature rises too high, then it can melt. and the components would cease to work. So the temperature unit raises an interrupt and it has to be handled. Again, in this case, the nature of the interrupt is that it is not expected. It can happen or come at any random time. So this was about the device interrupts which were random in nature. In the previous slide, we talked about some interrupts which were kind of expected. In this case, it was the operating system who had initiated some operation and was expecting the interrupt when the operation was complete. Other example we talked about was the timer interrupt. Again, here the operating system had programmed it to raise an interrupt after every few milliseconds, right? But in opposite to this, in contrast to the expected device interrupts, we also have some device interrupts which are random in nature. So this was the different types of interrupts and the different sources that can happen in the computer system. So the last thing that I want to talk about in this video is to discuss the differences between hardware versus software interrupts. So let's take a look, right? So as you can see in this table, so first of all, the examples we have already come across, right? The basic difference between a hardware and software interrupt is obviously the source of the interrupt, right? In case of hardware interrupts, the source of the interrupt is a hardware device, an IO device, right? It could also be like we have taken the case of the battery or the temperature sensor or the timer. It is not necessary that it be a IO device. It can be any hardware device, right? And the for software interrupts, the source of interrupt is the software, right? The user process which is executing. That is the source of the interrupt. So the examples that we have already seen is that in case of hardware interrupt, the example is the device interrupts that comes from a variety of hardware devices, right? And for software interrupt, the examples are system calls and exceptions. In system calls, the source of the interrupt is the user process who is invoking the system call, right? And in case of exceptions, again, it is the user process which is misbehaving, which is causing the error, which is the source of the software interrupt, right? And here the next thing is about whether the interrupt is external to the processor or within the processor, right? So when we speak of hardware interrupt, the device is coming from outside the processor, right? There are several components that make up the computer system, and CPU is one of the components. Apart from the CPU, there are a lot of IO devices and other electronic chips. So in case of the hardware interrupt, the interrupt is coming from external to the processor, from other components, right? Whereas in the case of the software interrupt, the interrupt is from within the processor, from the user process which is executing on the CPU. Whatever software is being executed on the CPU, that is the source of the interrupt. So this is also another difference between hardware interrupt and software interrupt. The hardware interrupt is external to the CPU, whereas software interrupt comes from within the CPU, right? And final difference is about the nature of hardware interrupt and the software interrupt. Hardware interrupt is asynchronous in nature, whereas software interrupt is a synchronous signal. So to understand this, we can think of it in this way. So when we talk about system calls or exceptions, the interruption is due to the activity that is being done right now, right? So the user process is invoking the system call or is misbehaving, that is causing the interrupt. So the interrupt is happening due to some synchronous activity. But if you compare this with the hardware interrupt, right, there the interrupt is coming from outside, right? We had discussed interrupt driven IO, and in interrupt driven IO, the user process which was being executed on the CPU, which is being interrupted by the hardware interrupt, has kind of no correlation with the interrupt, right? The interrupt is coming from somewhere else, from some other asynchronous activity. The asynchronous activity was the IO operation that was going on in parallel, right? So computation as well as the IO operation were going on in parallel in case of the interrupt driven IO. And when that IO operation finished, it interrupted the user process which was executing on the CPU. So this is a kind of an asynchronous interrupt, right? So these were all the differences between the hardware and the software interrupt. So guys, this was it for this video. We discussed the concept of interrupts. We talked about hardware and software interrupts, right? And we also discussed the concept of interrupt driven IO. Finally, we talked about the different kind of device interrupts, that is expected and random interrupts. And finally, in the last part, we compared hardware interrupts with software interrupts. So guys, this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.